we skipped a couple of sections. So we're starting with 4.6, and this is our unit on related rates. And so you'll see the two sort of core things that we are going to cover in this section. It's going to be a lot of word problems. So we're going to be bringing back the implicit differentiation most of the time with respect to t. So we'll be implicitly deriving with respect to time. And then the word problems where we have to actually come up with how these multivariables relate to each other. So we're going to need to come up with the relationship that connects these variables together. Before we jump into the related rates problems, let's just take a slow, friendly example. So let's say that we were given this equation, x plus 3y equals 7, and we want to differentiate it with respect to time, meaning time is going to be the independent variable that we're working with here. So that means, folks, that we want to implicitly derive every variable that isn't t. So we have to implicitly derive x with respect to t and y with respect to t. And if we did that, our equation would look like this. dx dt, and some of you prefer x prime, but I like this because it reminds me that I'm taking the derivative of x with respect to t. At any rate, plus 3 dy dt equals 0. It's telling you that these two things are working at different rates with respect to time. So in a word problem, we'll actually see how this all makes sense. Let's look at this practice problem. We are given this ladder, and it's 15 feet long, and it's leaning against this building so that end x is on level ground. So that's our x, and y is up against the wall. So we've got our x and we've got our y. And then they tell us that x is moving away from the building at a constant rate of 1/2 feet per second. So that's the rate at which x is changing with respect to time, feet per second. All right, so they're asking us in this problem to find the rate in feet per second of change of y, of the length OY. So they're saying now, how is OY changing when x is 9 feet from the building? That's a lot of information to process. So our first objective, folks, is we want to come up with the equation that relates x and y. So you're looking at this right triangle with sides x and y and hypotenuse 15. How can I relate those two variables x and y? I hope that you thought Pythagorean theorem. A squared plus b squared equals c squared. That's how I can relate my x and my y. All right, so that's our first objective. It's usually going to be either some sort of geometric equation that they usually give you, or something that is pretty straightforward, like if they're talking about perimeter or area. At any rate, so now we want to look at the specifics. What are they giving me? What have they told me verbally in this problem? They told me that they want us to find the rate at which y is changing when x is 9, and we also know that x is changing at that constant rate of 1/2 feet per second. So I know x, and I know dx dt, and they're asking us to find the rate at which y is changing. So they're asking us to solve for dy dt. Well, I think the one thing that's missing is we don't know y, or do we? If I know that my x is 9 and my hypotenuse is constant, then I can either Pythagorean theorem that out, or I know 9, 12, 15 is one of our 3, 4, 5 triples. So here we go. I'm going to erase the green stuff. And I think we're now ready to implicitly derive this equation, x squared plus y squared equals 15 squared, with respect to time. And if we did derive that implicitly, we would have this, 2x dx dt plus 2y dy dt equals 0. Now comes the personal preference. we can either isolate dy dt, since that's what we're trying to solve for, or you can plug in all of the information that you already know. I'm going to get dy dt by itself. So I'm subtracting the 2x dx dt over to the other side. And then I'm going to divide both sides by 2y. And then I just pulled out that 2 from the top and the bottom, and that left us with negative x dx dt over y. Now I can plug in all of my information. So I can plug in 9 for x, 1/2 for dx dt, and 12 for y. And since it said, find your rate in feet per second, it's okay if I leave my answer as -3/8. Let's take a quick minute just to express or talk about what that actually means in part A. So they're asking us to find the rate of change of y, and they gave us all of that other information when x is 9. And then we found from there that means y is 12. And we found that dy dt is -3/8. So that means that, as your x is slowly dragging away at that constant rate of 1/2 feet per second, that means x is growing at that rate of 1/2 feet per second. But as that's happening, our y, that y value, that height, is shrinking. That's why it's negative, right? Our y is decreasing at that rate of 3/8 feet per second. Let's look at B. So now they're asking us, let's find the rate of change in feet squared per second of the area. So now we're no longer using our Pythagorean theorem to tie this in, because they're asking us to find the rate of change, and with respect to time, of the area. And I know that area is 1/2 base times height. Oh, I erased. So here, I know my A is equal to 1/2 xy. They're asking us to find dA dt, the derivative of the area with respect to time. So I can look and I can see, I can still use the information from the previous problem or part. I know my x is 9, I know my y is 12. I know if I need it, and I will, that dx dt is 1/2 and dy dt is -3/8. If we want to derive that equation, A equals 1/2 xy with respect to t, I'm going to need to just take the derivative of A with respect to t. But I'm hoping that you can see in the 1/2 xy, we need the product rule. I'm going to pull out that 1/2. And so our equation should look like that. That's our g f prime plus f g prime, and then all times 1/2. And I believe we now have everything that we need, so we can plug them in. So we plug in 9 for x, our -3/8 for dy dt, 12 for y, 1/2 for dx dt, and we clean it all up and we get 21/16, and we can leave it as 21/16 since it did say find the rate of change in feet squared per second. Or if you just wanted to put it in there to be safe, tis fine. We're going to do bits and pieces of problem 2, and I uploaded the solutions to all of these so you can look at them if you're interested in just doing some extra work. Let's look at the givens in 2. We have a point, and I've got this sketched here. That's my x and that's my y. We've got a point P that moves along the graph of y equals √x in such a way that its x-coordinate is increasing at a rate of 2 inches per second. What does that tell me? That my dx dt is 2, positive 2, because it's increasing. All right, then I'm skipping A and B. Let's look at C. A line is drawn that joins P to the origin. I drew that green line. At what rate is the angle formed by ray, I'll put an O here for origin, OP, so let's call that angle theta. So at what rate is the angle formed by OP and the x-axis changing when x is 4? So what are they asking me, folks? They're asking me to find d theta dt, the rate of change of that angle theta with respect to time, when x is 4. So here's what we can do. We can drop that hypotenuse, and we can label the two sides of that triangle in terms of x and y. And then since we knew that y is root x, that helps. Here's my question. What is the, so our next objective is, if I need to find d theta dt, I need to come up with an equation that relates my theta to my x. What equation relates my theta to my x? Think about it. And I hope that you thought TOA, tan of theta, equals opposite over hypotenuse. And since I'm going to be deriving, I'm going to simplify root x over x to be x to the negative 1/2. Perfect. Now what's happening? Oh, and now we're going to implicitly derive that equation with respect to t. And we end up with this. Right? We've got our implicit, so tan theta derived is secant squared theta, but times d theta dt. And then the right side is our power rule. So I hope that makes sense to you. But it also looks as though we're going to have to find those three sides of our triangle. Secant is the reciprocal of cosine. So I'm going to need the hypotenuse and the adjacent side. So I just rewrote it so d theta dt is by itself. And let's use this piece of information. So I think we know if this x is 4, this side is 2, and the hypotenuse would be root 20. Okay, so let's plug in everything that we know. So we've got negative 1/2, our x is 4, so that's 4. I'm going to rewrite that as 2 squared. That'll help me with the negative 3/2. So unsimplified, it looks like this. When we clean that up, we end up with that algebraic mess. And remember, if they're just asking you what the rate of change is, you could keep your answer just like that. And then our units are in radians per second. That's our angle measure for our trig, always in radians. Let's look at this problem. This one I pulled from Delta Math. So we're given the volume of a sphere is increasing at a constant rate of that. So immediately, I'm hoping you know our dV dt is 1,172 cubic centimeters per second. Fine. So then, at the instant, r is 10, what is the rate of change of the surface area of the sphere? And you'll see they give you surface area formula, volume formula. You don't have to have those committed to memory. They're asking us in this question to find ds dt. Here we go. So how do I start this problem? I'm going to work with the information that they provide us. Again, they verbally told us the rate of change of volume, so we're going to start with the volume equation. And we're going to implicitly derive that with respect to time. And we get 4 pi r squared times dr dt. Okay, so what do we know? We know dv dt and we know r. So in this problem, we can actually find what dr dt is. Our dr dt is that number. And we need to round at the very end, so we're going to use our calculator and we're going to stow that value. Everybody remembers we can go to alpha y equals and choose option 1 and then type in what our dr dt is. It's that number. So we hit enter, and remember we've got that stow, so we can store, so I hit store, and then I'll store it into A. So now we're going to go back to that problem, and we're going to introduce the surface area equation. We know that S equals 4 pi r squared, so now we're going to implicitly derive that with respect to time. And we end up with ds dt equals 8 pi r dr dt, which when we plug in r and the dr dt should look like that. So now we go to our calculator and we type in 8 times pi times 10 times that dr dt. And our answer, oh, we didn't even have to round because those pi's cleaned each other up. Our answer here is 234.4.